Hello, I am Pat Hindle, Media Director at Microwave Journal. Let me introduce Dr. Alexander Chenakin, Director of R&D at Enritsu Company.
Hi everybody, my name is Alexander Chenakin. I am Director of R&D at Enritsu Company.
Enritsu has recently introduced rubidium signal generators. What is rubidium?
Rubidium is a brand name for our new signal generators covering 9 kHz to 20 and 43.5 GHz with phenomenal, absolutely unprecedented performance such as frequency stability and signal purity. To be specific, the rubidium signal generators achieve -140 dBc per Hertz at 10 GHz output and 10 kHz offset, which is better, actually way better compared to traditional instruments currently available on the market.
But why rubidium?
A rubidium atomic source is the heart of the instrument, but in a more general sense, this is a collection of very clever, I would even say unique solutions we collectively call the rubidium technology.
What is unique about the rubidium technology?
As they know, the main job of any frequency synthesizer is to create a signal from available reference. This may sound simple, but in reality, any method creates some artifacts called spurs. In addition, the main signal is normally not quite stable, but rather moves around. And this is called frequency instability and normally described in terms of Allen deviation. In addition to this, the signal can move faster, so our eye and available equipment cannot catch it statically anymore. So it appears as noise fluctuations called phase noise. Well, long story short, the job of designing any synthesizer is to minimize these effects. And I can say our design is doing this job quite good. I would even say disgustingly good.
Can we dive deeper into the detail? What method did you use?
To answer better this question, let's evaluate a simplified, very simplified block diagram of the rubidium synthesizer core. The main component here is a broadband YIG oscillator that covers 2 to 20 GHz frequency range with very low noise at high offsets.
Do you use commercially available YIGs?
No, unfortunately, no commercially available YIG oscillator can support our pretty tough phase noise requirements. Plus, they are quite expensive. That's why we designed our own YIG oscillator. It's called eSphere. Here it is. It provides low phase noise, -170 dBc per Hertz at high frequency offset. And even more important, we have a full control over this key technology.
Got it. Let's come back to the rubidium block diagram.
Okay, now we need to lock the YIG oscillator to wash out its phase noise at lower frequency offsets. The signal from the YIG is down-converted in a direct analog down-converter, which is essentially a chain of mixers driven by their own low signals generated by direct analog means. Long story short, essentially we create a direct analog synthesizer to lock a YIG oscillator to a desired frequency.
What are the advantages of your approach?
very, very low phase noise. As you know, any PLL component's noise is degraded by 20 log n, where n is a division factor within the PLL loop, and this degradation is quite substantial. So, in our case, there is no divider and absolutely no phase noise degradation.
That's a clever solution.
Yes, thank you. But that is not all. As you can see here, in addition, there is a multiplier inside the loop. This may look funny or even counterintuitive, but it works exactly opposite to a hypothetical frequency divider, meaning that instead of degrading, it's rather improving phase noise using the same 20 log n rule. In other words, let the main synthesizer issue work for us, but not against us.
That sounds great, but what are the limitations?
Well, we still need to obey laws of Mother Nature, or laws of physics, if you will. In this case, our limitation is phase noise of available reference.
I can see 4 signal sources in your block diagram.
Yes, they are built using different technology and squeezing every drop of phase noise at different frequency offsets.
I see a rubidium source in your block diagram. Does it perform better than a conventional ovenized crystal oscillator?
Yes, that's the thing. Any crystal oscillator utilizes a mechanical resonance, or in other words, it depends on dimensions. Hence, introducing an atomic status improves our time stability radically, not in times, but in multiple order of magnitudes.
Great. What about other important parameters like spurs?
Good question. Interestingly, the method we just discussed works equally well for spur suppression too. As a result, we have a very clean signal with no or minimal artifacts.
How do you protect such a clever technology?
Well, obviously, we do all kinds of precautions, such as patenting and so on. But frankly, if somebody wants to replicate or re-engineer something, they will be always able to do so. In my opinion, there are only 2 things which do work in this regard. First, people. You need to have right people who can draw, not just draw a schematic, because it's simple, quite simple, but rather have somebody who understands the whole concept, the whole new technology. And the second factor is time. In order to replicate something and bring it to a product level, obviously you need time. But in the meantime, we think about new things, new technologies, which are beyond of our current horizon. I believe here at Enritsu we have a very strong team, and I'm proud to be a part of it.
Alexander, thank you so much for explaining all the details. I'm sure the product's going to be very successful in the market, and we look forward to catching up with you again.
Thank you, Pat. From my side, I would like to thank you for the opportunity to share some of my thoughts. I would like to thank you and all Microwave Journal's readers.